So let's talk about our star, the sun. These lecture slides are actually from Dr. Kavan Ratnatunga. I'm using it. Dr. Kavan, some years he was here talking to you guys, the students, about various topics in astronomy. So in this lecture, we are going to briefly look at some basic facts of the star, our sun. Energy generation, maybe you have studied in A-level physics about hydrogen to helium fusion. We just want to look at it again. Internal structure, the sunspot cycles, things that you have heard at least. And the differential rotation is mechanics, right? Basically, magnetic fields, electric currents flowing because the charged particles flow, etc., and how it affects us here on Earth. Okay, so not very technical. So I just want you to look at some of these numbers and try to remember some of them, not all of them, obviously. So it's interesting to see that the distance from the Earth to the Sun is not a constant. Okay, it can be maximally 152 million kilometers, minimally 147 million kilometers, right? Because we are on an orbit, elliptical orbit around the sun, right? So we get closer to the sun at some point, and after 6 months or so, we are on the other side, right? That's interesting thing. The difference is about 6 million kilometers. So because of this distance, the light takes 8.5 minutes to get here. 8.5 minutes. So let's say you take a photograph of the sun. Okay, that photo is 8 minutes old. The moment you see it on your camera, what you see is the sun 8 minutes ago, not now. Not now. If anything happens on the sun, for you to see it, even though you see the sun all the time, if anything happens over there, right, something visible, you see it 8.5 minutes after, because light is traveling. Even though we know this, light takes time, its speed is finite, it doesn't take usually occur to us, right? Whenever we do our normal things, it's like instantaneous. Because the distances are not that great, we don't see the time delay, right? But when you take photos of the celestial bodies, the stars, sun, etc., you're dealing with very, very long distances, and then the speed of light being finite is going to be visible. Okay, so it's an interesting. If you look at the mean angular diameter, like from left to right or top to bottom of the sun, what is that angle? It's like 32 arc minutes. If you stretch your right hand or left hand and your thumb up, so that is roughly about 32 arc minutes, like half a degree, roughly. So you can close the entire sun with your thumb. And interestingly, this is very similar to the angular diameter of the moon, right? The size of the moon and the size of the sun in terms of angular diameter, as you see it from the Earth, is pretty close to each other, half a degree. So other things I don't want to go one by one, but few things. If you look at what the sun is made of, it's basically hydrogen, 74% hydrogen, 25 helium, hydrogen, helium, 1% other elements. Now, if you look at here on Earth, right, we don't have that much hydrogen and helium, okay? we have nitrogen and other materials, right? So they have all come from this 1%, right, which is common everywhere. So how come this 1% material of this 1% got together to form the Earth and the other, not only Earth, the other bodies like Mercury, Venus, etc. Right? There's a lot of other material, not hydrogen and helium. Again, there's no wonder because if you follow the dynamics, the evolution, it's a long story, right? There are different phases in the evolution, and this separation happened. Rocky dwarfs and gas giants, separation took place at some point, like filtering of material. Okay. What else is important? Luminosity. There you are. 10 to the 26 watts. Huge amount of energy coming out of the sun. Of course, here on Earth, we don't get this much. We get a very little amount because all the other energy is going out to the space. Okay. The location is about 8,000 parsecs away from the galaxy. 8,000 parsecs. And the other thing is, if you look at the speed of the sun, right, because when you talk about the cosmology, right, the universe, everything is moving with respect to something else. And there's no absolute reference, okay? There's nothing called stationary thing or something that is not moving at all. Everything is moving, and the motions are measured with respect to something else, the higher system. Say, for example, the speed of the Earth is measured with respect to the sun. And the speed of the sun is measured with respect to the galaxy. It's like that. So with respect to the galaxy, if you take galaxy as a constant, right, and the initial platform coordinate system, the sun is going around it at 220 kilometers per second. 220 kilometers per second. Blink of an eye, 220 kilometers. And it brings all of the members together with it. Okay. Now, let me show you the energy emission of the sun. It's just like this. Now, according to Wien's law, you can actually draw the ideal curve, black body radiation curve for temperature 5,800 Kelvin. So this is 5,800 Kelvin line. Our sun or any other body, right? It will have this curve. Okay. And if you take measurements, right, using filters, etc., you can plot this one. So it's not close, it's not comparable to the ideal black body curve, but you can see very close resemblance, right? So this is exactly what we want to have. And there's a certain gap over here that is of a concern why it's happening like that. But other than that, is fairly a good fit. Okay. So the surface temperature is like 5,800, maybe slightly different. And the maximum wavelength, the wavelength of the maximum energy is somewhere over here, right? So interesting. Now, how does it generate energy, right? Glowing out and foster life on the earth and everything, right? So that is the next topic. The total energy output is, as we discussed, 10 to the 26 watts. And all of this energy is coming as high energy photons, right? Photons, particles like light from the sun. And the process of generating this energy is hydrogen fusion. You have heard of that. It occurs only at temperatures in excess of about 10 to the 7 Kelvin. So you need to have about 10 million Kelvin. This is another interesting thing to remember. If you can generate 10 million Kelvin in a reactor, you can actually start hydrogen fusion, right? So in the sun, it happens in the dense hot core. So if you look at the initial nebula hypothesis, when the nebula contracts, the temperature inside the nebula increases, and when it crosses the point 10 million Kelvin, it starts hydrogen fusion. So that's all. That's how it happened. Now, hydrogen is matter. Hydrogen turns to helium in that process. Helium is also matter. And using matter, you get energy out. Matter to energy. How do you calculate how much energy you are going to get from a chemical reaction which has matter input, matter output, right? And that is described by the Einstein's very famous equation, the number one equation in the world, most famous equation, E equals mc square. Okay, so we are going to look at this maybe next class. So I would like to stop over here for today. And as I explained, check Moodle tomorrow by noon or so. Material will be available for you to download and refer, or just run it on Moodle itself. Lecture notes will be available, and the assignment, right? Take the assignment and work it out and upload back to Moodle within a week, right? Because after that, it automatically closes. You won't be able to submit any more, okay? So keep that in mind. Any questions, please?